Hi, so this is lesson 13 on equilibrium. This is the first lesson in section number 3. So this won't be on test 2, which is on May 11th. All right, so just a few things on the schedule. This will be posted on May 4th, so you can see here the Zoom schedule for that week, including May 6th. We have quiz number 2, which will be on Blackboard. Homework 10 through 11 are due on Sapling. These are all on kinetics. There's a survey on Blackboard, which closes on Wednesday, May 6th. This allows us to understand what's working, what's not working. Test number 2 is May 11th. It is on lessons 7 through 12. That's kinetics, and it's going to be on Sapling, similar to test 1 procedure. Okay, there's no homework for this lesson because it would be due on the same day as the test, but there may be some stuff on homework number 14. Just a little bit more on the quiz. You already did a quiz. It'll be very similar to that between 2:40 and 4 p.m. There'll be 2 to 4 problems, some on rates and differential rate laws, and then one on integrated rate laws. This one for sure will be one where you have to work out, whereas these might be multiple choice. We'll see. All right. So yeah, let's do a review of last time. Mechanisms. Mechanisms is the last topic that will be on test number 2. And so we have here a reaction progress diagram where we go from the start of a reaction to the end of the reaction. And this kind of tells us the energy associated with this, right? So we have some things that are low energy and high energy. So we want to know where the reactants are and the products, and then this transition state. The reactants are what we have at the beginning of the reaction, products at the end, okay? And in between, we have that transition state. Going from reactants to transition states, that's our energy of activation, okay? This will always be positive. It's always going to have a hill here, right? The difference between reactants and products, that's our delta H. Now, sometimes this can look like this, or sometimes it'll be like this, where products are actually higher energy than reactants. Okay, so let's move on. For test 1, we covered thermodynamics. Okay. In test number 2, we studied kinetics, and we also dealt with mechanisms. Now we're going to move on, and we're going to talk about a topic called equilibrium. We're going to be covering equilibrium for almost the entirety of the rest of the quarter. And we're going to talk about equilibrium generally, and then we're going to move on to acids and bases. Okay, and this will be what will be covered on test 3. Okay, the final will cover everything because it's cumulative. Plus, it'll deal with a few other things like precipitation. Okay, so equilibrium is when we have a reaction going one way and going the back, right? We can have liquid water, we can put it in the freezer, we can freeze it. We can then take it out and melt it, right? This is a reversible reaction. So let's look at this. So let's say we have A plus B going to C plus D, and it has some rate constant, right? K. Remember, small k is rate constant. K is going to be confusing, so we need to make sure we differentiate between them. So small k, this is in kinetics. Okay, most reactions, actually all reactions, are reversible. So I can go C plus D going to A plus B. I basically just turn my reactants into products, my products into reactants. And this will have a different K. Here I've signified it as K negative 1. I could also signify it as K2, etc. So we can basically take these two reactions and say A plus B has a reversible reaction going to C plus D. Okay, all reactions are reversible. All reactions will be able to go both ways. But it turns out that some reactions are so favorable in one direction, right? So a lot goes in this direction, just a tiny bit back, that we think of them as nearly reversible. Okay. or nearly irreversible, meaning that they do not go back. Okay, so let's think about this, right? We already talked about we have H2O liquid, we put it in a freezer, we get solid. We take it out at room temperature, we get liquid again, right? So H2O liquid goes to form H2O solid, and this is a reversible reaction. There are some other examples, in biology. When we think of hemoglobin is what basically bonds to oxygen. So this is a hemoglobin molecule, right? It has iron in it. This is one of the reasons why we need iron. And so what happens? That iron bonds to the O2. Well, luckily for us, excuse me, luckily for us, this is a reversible reaction, right? Oxygen goes onto the hemoglobin in the lungs, and then the hemoglobin transports that to the cells, and then the oxygen comes off, right? It's a reversible reaction. In lab, we also see this, right? When we do titrations, right? When you do titration, you start to see a color change, and then it goes away. This is an example of a reversible reaction, right? You're starting to form that pink compound, and then it reverses back. Okay? All right, so now let's go ahead and look at it on a microscopic level of what's going on. Let's say we have this reaction here. A goes to B. And so if we were to start off at 0 seconds, so time equals 0 seconds, and all we have is A, okay, what's going to happen? Well, some of this A is going to just turn into B, right? So let's say this one turns into B. Okay, notice no B can turn into A because there is no B, right? So I can't have this reverse reaction, okay? So I can say that at the beginning, I have some A, and I lose some, so my molarity goes down. I have no B, so my molarity goes up, okay? All right, now at 1 second, I now have some A. I have a lot of A, but I have a little bit of compound B, okay? So what can happen? Well, because I now have some B, I can now have that reverse reaction occurring. I can have some of this B, the green dot, transferring back to A. And now look at the A's. I have less of these A compounds, the black spheres, right? So my forward rate is going to actually slow down, okay? So what's going to happen is, remember, when we were talking about rates, the slope tells us how fast something's going. So notice these start to slow down as I get closer, as I go along. Okay, 20 seconds. Now I have some more B that's formed. I have less A, so my forward reaction continues to speed up, but my reverse reaction slows down, right? Or sorry, my reverse reaction speeds up because now I have more B, so this reaction's going to go faster. I have less A, so this is. Okay? But still, I have more of my reactant A, so I still have more, so my rate forward is still going to be faster than my rate reverse. Okay, so over time, this is what happens. My amount of A decreases until it kind of comes to the state where it stops changing. And my amount of B increases until it comes to a point where it stops changing. This is what we call equilibrium. Okay? It's the time when the forward and reverse reactions occur at the same rate. So A is turning to B at the same rate as B going to A. Okay? The concentrations don't change, but they're not necessarily equal. Notice at this equilibrium, I have more A than I have B. That's totally possible. And what we've learned is that if a reaction is not at equilibrium, it shifts towards equilibrium. This is a key point, right? So if I have a reaction not at equilibrium, it will go towards equilibrium. All right, one thing is, let's say at 100 seconds, we're at equilibrium, concentrations are changing, or aren't changing, are not changing. But both of these reactions keep on occurring, right? This black compound A could turn into compound B, and this compound B can turn into compound A, right? But the key thing is the rates, the speeds at which these two reactions occur are the same. Okay? An example is water. Okay, this water freezing, right? What's happening at 0 degrees C, which is the freezing point, is some of this water is freezing, right? So this water right here freezes. But at the same time, some of this ice melts, okay? And it's equal amounts such that it looks like it's staying constant. Here's another example from the book. Let's say we have these two guys and they're juggling, right? At any given time, this guy has two juggling, whatever they're called. This guy has two as well, right? But this one is going to go over here. This one's going to go over there, right? So they're changing as they go, but at any given time they have two, right? So the reactions going this way and this way are both occurring, but at any given time they have two of these juggling staffs, okay? All right, so we can ask ourselves, how do we determine what concentrations we're going to get, okay? Well, this depends on the reaction, okay? And we're going to go through over the next week how we determine what these concentrations are. Now, before we do that, we should label two things. We have what we call homogeneous equilibrium and heterogeneous equilibrium. Homogeneous, remember we've used the term homogeneous a lot. We've talked about homo. Homo means the same, okay? So homogeneous equilibrium is equilibrium where all compounds are in the same state, right? So for instance, this one here, we have I2 aqueous plus I minus aqueous going to I3 minus aqueous, right? Now this means, in practice, that means they can either be all aqueous or gas phase. You're not going to have it if they're all solids, and typically not if they're all liquids, usually aqueous or gas phase. We can also have heterogeneous equilibrium. Hetero means different, okay? So that's when we have an equilibrium with more than one state, right? For instance, here I have calcium 2 plus aqueous plus 2Cl minus aqueous goes to form CaCl2 solid, right? This is heterogeneous. This is homogeneous. Okay, that's going to become important once we start talking about something called Q. Q is called the reaction quotient, okay? Now we can talk about Q in two ways. We can either use concentrations or we can use pressures. If we use concentrations, we call it QC. If we use pressures, we call it QP, okay? And so like we'd use pressure for gases, we'd use concentration for aqueous. Now it's the ratio of products to reactants, and the key is, so if I have a reaction like this, AA plus BB goes to CC plus DD. I put the products on the top, so they're concentrations, and I raise each to its coefficient in front. And then I do the same thing for my reactants, raised to their coefficient. Okay. I know this is different than what we learned in kinetics. In kinetics, I said you can't do this. In equilibrium, you do it, right? Why is that the case? It's because they're different topics. So you need to realize that, okay, when I'm dealing with kinetics, I'm dealing with one set of rules, equilibrium, a different set of rules, right? Because they work, here we're looking at the stoichiometry. Okay? All right, now in this class, we're really only going to talk about concentration, so you don't even have to worry about this. But just know that, hey, I can use pressures or I could use concentration. Okay? And we're just going to call it Q, right? We're not going to call it QC. I'm just going to call it Q. All right, now one thing that's important is that all must be in the same unit. Okay? Molarity if I'm talking about concentration, or atmospheres if I'm talking about pressures. But Q itself is going to be unitless. Okay? Q has no units. Okay? So I use molarity for all these, but I get out in the end, I get a unitless number. Okay. Like I said, here we'll use molarity. By the way, it may seem weird to think of molarity for gases, but remember molarity is moles per liter. And I can rearrange PD equals nRT to get N over V equals P over RT, right? And what that means is, oh, we know we can usually know its pressure. So if I know its pressure and its temperature, I could figure out its molarity. Okay, there's one last thing for reaction quotients, and this is a big one. If you have any solids or liquids, they are not in the reaction quotient. In their place, we give a 1. The reason for this is, remember, concentration is the moles of one compound over liters of the total. Well, solids are pure. They have no concentration. Liquids are pure. They have no concentration. So in their place, we just use 1. All right, so we only use concentrations for aqueous or for gas. Okay, so reaction quotient, ratio of products to reactants, okay? Only gases or aqueous, solids and liquids I put as 1. All right, now Q tells us how far to the right, okay, a reaction is, okay? Because think, if I have a high Q and Q equals products over reactants, if I have a big Q, that means I have more products, right? So that means this reaction is shifted towards these. If I have a low Q, that means it's shifted towards reactants. I have more reactants than I have. All right, so let's go ahead and let's do some problems. So Q equals, we have products over reactants all to their different coefficient. So let's say we have this problem. So we have this reaction here, and we want to know the equation for Q, and we want to figure out the value for it if the concentration is 1.2 molar. All right, so on the board, I can write down that equation for NH3 aqueous plus 7O2 aqueous goes to form 4NO2 aqueous plus H2O liquid. How much was that? 6. All right. So I have this reaction. So if I want to know Q, I take products over reactants. So that'll be the concentration of NO2 to the 4. And we need to be really careful, right? Last couple lessons, I haven't been talking about the states very much because when we're talking about kinetics, it's not as important, right? Here it is. I just put a 1 in the place for the H2O. Okay. The reason being is that this is a liquid, so it doesn't show up. And in fact, seeing that I have a 1 there, I often just leave it off. Okay. And then I do NH3 to the 4, and O2 to the 7. Okay. Now I can plug everything in. I can have my, I'm told here that everything's 1.2 molar. All right, let's see. By the way, on your calculator, we all know how to do that x squared button, hopefully, right? So I have 1.2, I do x squared. That gets me 1.44. On my calculator, it's 1.2, this y to the x. So I do that, and then I put in 7, and, oh, sorry, it's 4, 1.2 to the 4. I get my answer, okay? All right, so your calculator may be a little different. Make sure you know how to do that, okay? I guess the old-fashioned way would be just to say, okay, it's 1.2 times 1.2 times 1.2 times 1.2. That's what to the 4th power means. But, you know, let's figure out how to do that. All right, this one is 3.583. I now... Two 2.0736 over 7.43, and that's going to give me 0.2. Okay. I started off with 2 sig figs, so I end with 2 sig figs, and Q does not have units. Okay, so do not put Q here. Just it is unitless. There are some things that are unitless. All right, so here it is on the board. Make sure that the first important thing is always to be able to remember that that H2O isn't there, okay? So I don't include H2O in my value. All right, let's do a few other ones, okay? Let's say we add Ca2 plus 2Cl minus going to CaCl2. We want to know the equation for Q and its value in all concentrations, right? So what we're going to do is we're going to say my Q equals products over reactants. All right, my reactants actually are fairly easy. That's Ca2 plus, and I have Cl minus, and I have to square this. But notice, my products, I have a solid. Okay? So I put a 1 in its place. Okay? And then I can go ahead and I can do the calculation. Okay? It's very important that you add this 1 here. Because if you don't, then you might think that, oh, my Q is just equal to calcium times chlorine or chloride squared. But no, this 1 here means that those 2 ions, right, calcium and chloride, are in the denominator, in the bottom, okay? Notice how in that previous one, it wasn't as important because I had this NO2 there, right? So I didn't have to include a 1 here, because that 1 didn't actually matter, right? But when I only have 1 product and it's solid, make sure you go ahead and you add that. Okay? All right. One other one. And this one, I'm actually going to do on the board again, okay? So this is a reaction where I have some gas species. So I have 2OH going to form H2O2. All right, and so I can plug in for my Q. So my Q is H2O2 over OH squared. Okay, they're both gases, so they both appear. And now when I do this, I can plug in my values. So I say this is 2 molar over 0 squared. 2 molar over 0 squared, that's 2 over 0. When I do that in my calculator, it's going to give me an error message. Okay? 2 divided by 0. It gives me an error message. Okay? That's because this is not allowed. Okay? You can't divide something by 0. Right? How many times does 0 go into 50? I don't know. Does it go in 50 times? Does it go in 1,000,000 times? It doesn't make sense. Okay? And so that's the right answer. But we should think of this value as something else too. Okay? 2 over 0. Let's replace that number, 0, with a really small number. Okay? If I put this into my calculator, I'm going to get something like 2 million, right? I'm going to get a really big number. And so I should think of this as being infinite, right? I have infinitely more product than I have reactant. Okay? If I have $0 and Donald Trump has $1 billion, he has infinitely more than I have, right? If I have $1, he has $1 billion, he has $1 billion times more than I have. But here, whenever I have something over 0, that means it's infinitely large. Okay? All right, so let's go ahead and let's have you guys do a problem. So this is using this equation here. We have an equation with 2 aqueous values, okay? Or 3 aqueous compounds. And we're going to use these to figure out our equation for Q. And then we have some data from time equals 0 and some data from later in a reaction. And we're going to go ahead and have you guys calculate the values for Q. All right, so that's video problem 13A. Okay, so I'm not going to do it here. You can do it afterwards. But these are the values you will get. You'll get a Q of 0 at the beginning, and you'll get, after 250 seconds, 0.45. And so what we can do is we can label these on something I like to use for equilibrium, and that's a number line. Okay? So a number line, remember, you learned about this in grade school. It goes from small to big, right? So Q can be anything from 0 up to infinite. Okay? Those are basically the ranges. We can't have a negative Q because we can't have negative concentration. Okay? All right. So at time equals 0, we had Q of 0. At 250 seconds, we had Q of 0.45. Right? So my reaction has gone from left to right. This side has all reactants. This side has all products. Okay? So it's shifted from having all reactants to having some product. All right, so now let's go on and let's think about that. Why does Q change? Well, it changes because over time, notice my O2 goes from 2.5 to 2.2. So my O2 concentration's changing. My SO2 goes from 1.2 to 0.6, so it's also changing, right? Well, eventually, it's gonna even out for both of them, or stop changing. That's called equilibrium. My SO3, it's increasing because it's a product, so it increases, and eventually it also gets to equilibrium. Remember, equilibrium is not when the reactions stop, it's when the concentrations stop changing. All right, so my Q value is changing with time, right? So my Q was 0 at the beginning, it increased, and eventually, once my concentration stopped changing, my Q value is also going to stop changing. This Q value at equilibrium, we call this K. All right, this is where I said it's going to get confusing. We're going to use a big K. And that big K represents the equilibrium constant. Sometimes they use K or KEQ to show that it's equilibrium. I'm just going to use K, right? Big K means equilibrium constant. And this is the Q at equilibrium. Okay? Sometimes it's also called KC or KP. You may see this in the thing. I'm just going to use big K, right? But if you see big K, it's an equilibrium. So anything else on there doesn't matter. All right. Now, the equilibrium constant is dependent on temperature in the same way that rate constant is dependent on temperature. Okay? We'll look at next time the effects of temperature on it. But what this says is that, hey, at a certain temperature, I'm going to get a certain ratio of products to reactants. Okay? All right, so like I said, using pressures, I get QP and I get KP, but we're just going to use that. Okay. So I think I have it later. The equation for K is going to be the exact same as the equation for Q. The only caveat is that all of these are now at equilibrium. So I can put an equilibrium sign on each one. Okay? I have this somewhere else. We'll see it. All right. So let's see. Okay? So remember we said we're going to use a number line where Q can be anything from 0 to infinity. Okay? We have reactants and products. If I have two reactions, I can have reaction number 1 and reaction number 2. They can have different values for the equilibrium constants. In this case, reaction 2 will have more products at equilibrium than reaction number 1. Okay? Reaction number 1 has less products or more reactants than reaction number 2. We can also, I said 0 is no product, Q equals infinity is all product. If I add Q equals 1, that means the reactants and products are about the same. Because remember, Q is products over reactants. Okay? So if I have 1, that means that these two things are the same. 50 over 50. 20 over 20. All right. So what I can say is that if I had a reaction and it had a K of 50, that would be one where I have more products than reactants. Okay, so now we're going to talk a little bit more about Q and K. And we're going to use this to figure out how reactions adjust to get to equilibrium. Remember, we said that at the beginning, that they adjust to get to equilibrium. All right. So let's say here's my Q and here's my K, right? My Q is less than my K, right? This could be 0.1, this could be 1, or whatever. Q is less than K. What's going to happen? My Q is going to go to K. Okay? Remember this. I'm going to say it a lot. Q goes to K. Q adjusts to get to K. All right. So it's going to shift right or form product to reach equilibrium. Okay. So that means what's going to happen in this case is some reactants are going to come together to form more products until we get to equilibrium. let's say we had the opposite case where we had Q greater than K. Right? So here, let's say that the Q is 2 and K is 1. What's going to happen is it's going to shift towards the left, forming reactants to reach equilibrium. Here's another visualization of this. Okay? Let's say that we have Q less than K, right? So we have more reactants than we should. What's going to happen is some of this B is going to go down, some of the A is going to go down. These are going to react, and that's going to form C and D. Right? And now I'd be at a place where, okay, this is equilibrium. But let's say in a different world, I had a Q that's greater than K, so I have too much product and not enough reactant. My products are going to go down, they're going to form reactants, and they're going to increase until I get to equilibrium. Right? So let's go ahead and let's look and let's understand this. Okay? So right now we're going to go through some problems to understand the direction of shift. And then in 2 lectures, we're actually going to go and we're going to understand how much they shift. Okay? All right, so let's say we have this reaction. Ca2 plus 2Cl minus goes to form CaCl2. Okay? And we're told at equilibrium, calcium is 1.1 molar and chloride is 0.9 molar. What is Ke? All right, so we have this equation, and we're told that we need to find Q, or we need to find K, right? So if I want to find K, that means I'm going to do 1 over calcium 2 plus, chloride to the minus squared, and these have to be at equilibrium. I'm just going to put an equilibrium. All right. Now notice that calcium chloride's not in there because it's a solid. Okay? Now, we have to be very careful. Okay? We have to be very careful when we do these problems. Okay? Because we're going to have to say, hey, are those concentrations we have there, are those initial concentrations or are they equilibrium concentrations? Well, in this one, we're clearly told that they're equilibrium concentrations. So I can just plug these in. There will come a day, and it'll be in 4 days, right, when I do that lesson, where we will not be given equilibrium concentrations and we'll need to find them. But for now, we're told these are equilibrium. So I can plug those in. 1.1 molar for the calcium, 0.9 for the chloride. I can do the math. 0.9 squared times 1.1. This will be 1 over 0.891. This will be 1.1. Okay. Remember, K doesn't have units. Okay. So this is the equilibrium constant for this compound, or this equation. Okay. Notice it was the same step that we did to calculate Q. The difference was we were told these were at equilibrium. Okay. So at equilibrium, we do the same equation and we get K. All right. So there we have it on the board. And so let's say now we're going to use that equation that we just did, that K equals 1.1. And a lot of times we just put it right next to it, so that tells us something about it. And now we're told that we have a solution with 2.05 molar calcium and 0.74 molar chloride. So now we need to find the Q. Okay? Now, what do? I do the exact same calculation, except notice it doesn't say anything about those being at equilibrium, right? These are just concentrations. So if they're just concentrations, we plug them in and we get our value for Q. This is 2.05 molar. This is 0.74 molar. That's going to get me 1 over 1.123. And that's going to get me 0.89. That is my Q. Okay? So that's my Q, that's my K. So my next step is, and I always just draw out a number line because I knew that. My Q is here, and my K is here. Okay? Q goes to K. Okay? Q goes to K. Okay? You need to remember this. This is key. I'll get questions asking, does K go to Q or does Q go to K? Q goes to K because reactions shift to equilibrium. This is not at equilibrium. This is at equilibrium, so we'll shift towards it. So what's going to happen? I'm going to shift towards the right. I'm going to turn some reactants into products. Okay? So some of this is going to react to form more of my calcium chloride. All right, so here it is on the screen. We figure out our equation for Q. We plug in our units or our concentrations, and we find our value for Q. Then we compare that to K. All right, why don't you guys do another one? This is the same equation, but now we're going to be able to calculate a new Q and figure out its shift. All right, so that's video problem 13B. Lastly, we're going to do one more with this, right? So we did one where Q was less than K. You're going to do one on your own. Oops, wrong color marker. Not that it matters. Dates are important. All right, so we're told that our third solution has 1.66 molar calcium, and we have 0.74 molar chloride. So I have there my Q equals 1 over calcium times chloride squared. So I can plug in the values. 1 over 1.66 times 0.74 molar squared. Make sure you're squaring the 0.74 and then you're multiplying by the 1.66. You're not multiplying these. Okay. So what I get as an answer is, let's go ahead and just do this just to make sure. So that's 1.66 times 0.5476. That's 1 over 0.909. And that's going to get me 1.1. This is my Q. So now I can compare my Q to my K. Notice that Q equals K. So what does that mean? We are at equilibrium. Okay? Being at equilibrium means that it won't shift. Okay? It is at equilibrium, so it is already done. All right, so here it is on the screen. We calculate our Q, we compare it to K, and we determine that shift. In this case, if Q equals K, there is. Okay, I wanted to show one other thing with this. We went ahead at the very beginning, or a couple slides ago, and we calculated K based on this data. 1.1 molar for the calcium, 0.9 molar for the chloride. Okay, we just went ahead and we looked at a different solution, 1.66 and 0.74, calculated, and we got that 1.1 as well, right? So this equals Q, but it also ended up equaling our K. What does this mean? I can get this value, 1.1, based on different concentrations, right? So I can have different concentrations, but the same K, right? In the same way that if I'm comparing two people's wealth, right? I have $1,000, Donald Trump has $1 billion. If I compare him, he has $1 million for every $1 I have, okay? If all of a sudden I now have $2,000 and he has $2 billion, he still has $1 million for every $1 I have, because it's a ratio, okay? So just because you have the same K doesn't mean your concentrations are going to be the same, but their math is going to work out to get that same ratio. Okay, so that is it for equilibrium. We talked about what equilibrium was, right? Basically, the concentration stopped changing, but the reactions are still occurring forward and backward. We talked about Q. Remember, solids and liquids aren't in there. And then we talked about K, which is the same thing as Q, but at equilibrium. Okay? And then we talked about shifting. The one thing I don't have on here is, remember that we talked about QP, QC, etc. We're just going to call these Q. Okay? And we talked about KEQ, and sometimes it's called KC, and sometimes it's going to call KP. We're just going to call these big K for equilibrium. All right, so that is it for lesson 13. Remember, there's no homework for this one, but some of these will be on homework number 14. All right, with that, I'll talk to you later. Have a good day.